Hi students, good morning. Welcome back to our physics classes. So we were talking about rigid body dynamics and we have stopped with the concept of couple, two equal and opposite forces acting through 2 points which are separated by a distance. Then we can say that that generates a couple. Then we have seen what is moment of couple and how you can calculate the moment of couple. So moment of couple is measured as one of the force multiplied by the perpendicular distance between the line of action of these two forces. So that is the concept of couple and moment of couple. Then you have already learned that total moment of forces is equal to, equal to zero. That means clockwise moments is equal to total anti-clockwise moment. So based on this equilibrium, so we already said that a rigid body is said to be in equilibrium when there is no force acting and where there is no torque acting. Both torque and force acting on a rigid body is equal to zero. Net torque and net force acting on a rigid body is zero. We can say that the rigid body is in equilibrium. So a special kind of problem is there in physics, that is ladder problem, leaning ladder problem. That means a ladder is placed on wall. Keeping on wall in a slanted direction, which means suppose you are having a wall here. On this wall, a ladder is placed like this. A very casual situation. We are keeping a ladder close to our wall. So that ladder is not slipping, which means it is in equilibrium. It is in equilibrium. So what are the forces acting on that? What are the forces acting on that? Or how you can say that it is in equilibrium? That we are going to discuss now. Okay, so we are starting with the leaning ladder problem, or simply the ladder problems. Okay, this is our ladder problem. See, here a ladder AB. AB is a ladder and it is placed slanting on the wall, keeping on the wall. And at the point A and B, which is in touch with the floor and the wall respectively, they are getting a reaction force. So here you are having a normal reaction which is acting in the upward direction, and here you are getting a reaction force RB from the wall, normal to the wall. Here G is the point of center of gravity through which its weight is acting in the downward direction. See, this is a force Fs. Fs is the friction force acting towards the point C, the foot of this wall, and N normal reaction and Fs are two forces are acting. So its reaction or its resultant is the net force at the point A, which is Ra, which makes an angle theta with the flow. So these are the forces acting on the ladder. These are the forces acting on the ladder now. And we can say that this ladder is in equilibrium. This ladder is in equilibrium. So to keep the ladder is in equilibrium, you can say that what is the force acting here? The force acting here, the point A is F is equal to Ra cos theta and N is equal to Ra sin theta. At equilibrium, Fs is equal to Ra cos theta and N is equal to Ra sin theta. Okay, so that is the along x-axis. Along x-axis, for equilibrium, it has to prove that it has to be satisfy that Fs is equal to Ra cos theta and N is equal to Ra sin theta. Okay, so for translatory equilibrium, delta Fx or sigma Fx should be 0 and sigma Fy should be 0. What is sigma Fx? Sigma Fx is the total force acting along the horizontal direction, that is x direction, and sigma Fy is the total component of force acting in the y direction. So along the horizontal direction we can have F and RB are acting. Fs is acting towards the right and RB is acting towards the left. You can see here Fs is acting towards the right and RB is acting towards left. In vertical direction, N is acting in the vertical direction upward and W is acting in the downward direction. So for the ladder to be equilibrium, in translatory equilibrium, we can say that Fs minus Rb is equal to 0 because Fs and Rb are acting in opposite direction. So the total force in x direction, that will be delta or sigma Fx is equal to Fs minus Rb should be 0. Fs minus Rb should be 0. That is Fs is equal to Rb. Okay, then sigma Fy is equal to, which are the forces acting in the y direction? They are N minus W equal to 0. So N is equal to W. So what is Fs here? Ra cos theta. So which is equal to Ra cos theta. And what is W? That what is N? That is Ra sin theta. Okay. So these are the conditions for translatory equilibrium. That means no force should be acting on the ladder either in x direction or in y direction. No force is acting on acting either in x direction or in y direction. Okay. Now one part of equilibrium we have discussed now, that is translatory equilibrium. For to complete equilibrium of this rigid body, you have to show that the total torque acting on it is also 0. Total torque acting on it is also 0. That means the total clockwise moment is equal to total anti-clockwise moment. So for that, which are the forces which can generate torque or moment that is, which are the forces acting when you are taking the moment of force about the point A, W is acting in the downward direction and RB is acting in the horizontal direction. That means W is acting in the vertically downward direction and RB is acting in the horizontal left direction. So minus W into AD. AD is the distance from the point A. We are taking the moment about the point A. So here you can mark the point T. So from the point, the line of action of this force W is AT. So since it is acting in downward direction, minus W into AD. You can write minus W into AD plus RB into BC equal to 0. That is due to the moment of total moment should be equal to 0. So we can write as RB into BC is equal to W into AD. RB into BC is equal to RB into BC equal to W into AD, where BC and AD are the perpendicular distance from the point about which we are taking the moment to the line of action of these two forces. Perpendicular distance between the line of action of these two. See, this is the point A and this is the line of action of RB. So the distance between these two is BC. This is the line of action of W. This is a fixed point. So AD is the perpendicular distance from A to the line of action of W. So that is why we are taking minus W into AD plus RB into BC. This is anti-clockwise and this is clockwise. So that is the net torque or net moment will be 0. That should be equal to torque equal to 0. Net torque acting moment is 0. Okay, so this is the condition for a ladder to be equilibrium. That means total force acting on this should be 0 and total torque acting on this should be 0. Clear? So that is the last topic in this chapter, rotational motion. That means rotational motion of a rigid body. That is moment of inertia.